Hi and welcome to this clip on the 2016 paper. It's actually the fourth one in a series that I've done in no particular order, so this now completes my clips on the 2016 paper and a 2017 paper. So each clip is one question. So at the beginning of each clip what I normally do is go through a little bit of advice, putting what's on the front of every single year's paper into some context for you. So the paper is slightly different from normal A-level papers in that it's more deductive and problem solving in nature. So it's not recall at all. There's some recall in your A-levels and also some deductive work in your A-levels. What this particular paper will do, this C3L6 style paper, will develop your deductive and problem solving skills in a chemical setting. So don't feel you have to go away and revise lots of different things from your flashcards or notes. It's more about looking at what's in front of you and applying a logical approach. So it's also very important to be clear in your workings and use the correct number of significant figures. As per normal practice in an A-level, the accepted protocol is to use the least sensitive piece of data in the question. So let's say you have the least sensitive piece of data has 2 significant figures. That's what you should give your answer to, even though you may have other pieces of data that would have 3 or 4 significant figures. So looking at the first part of the question, it'll be familiar and accessible, just like any Cambridge Chemistry Challenge question. This is designed to sort of not put you off and put your mind at ease, so that you can be, busy and get going and have a momentum when it starts to get a bit harder later on. And what they'll also do is give you some contextual information about the compound they're going to ask you about. This helps to set the scene so that you can see the point of the compound in the question. It helps your mind sort of link with it in a slightly more emotional sense. So part A says, knowing the 2 common oxidation states of iron, what are the possible oxidation states of the titanium in ilmenite FeTiO3? So you may not have come across them yet if you're first year, but you've probably heard of iron 2 and iron 3, iron 2 oxide, iron 3 oxide. So it goes without saying that iron 2 would be iron 2 plus and iron 3 would be iron 3 plus. So I'm working on the assumption that you're reasonably happy with that idea. And we also know from the question, because it says it just above, that titanium forms TiO2, which is titanium 4 oxide, and it talks about titanium 4 chloride, so it's already suggesting quite strongly that titanium forms oxidation states of +4 as well. And if you go to the periodic table that's provided with the paper, you'll see that titanium and iron are D block elements and are filling the 3D subshell. So we've collected a few bits of information there that will help us work this out. So they're asking for FeTiO3. So the best thing to do is start with the thing that we know. We know that oxygen has an oxidation state of -2 in the vast majority of cases. There's no reason to assume there'd be any different here. They're not trying to trick you. If there was a reason for it to be different, they would have told you. So because they haven't mentioned anything about oxygen, you assume that it's -2. So 3 lots of -2 makes a -6. The whole thing is neutral, so iron and titanium have to add up to +6. So if we start by taking iron to be the +3 oxidation state, we can obviously then say that titanium is also going to be +3. If, however, the iron is +2, then to make it up to neutral, titanium has to adopt +4. So therefore that allows us to write out our answer. So now we can move on to part B. So this next part is simple equation balancing. It tells you that titanium 4 oxide, chlorine and carbon react to make TiCl4 and CO. So all you have to really do is watch out for the fact that there's 4 chlorines on the right hand side. So you put a 2Cl2 on the left. Same idea with the next one. This is the compound we've just worked out the oxidation states for. So I'm slowing down a little bit here because FeTiO3 is a slightly more complicated compound than TiO2. There are also 2 different possible oxidation states that the titanium could be in. So it's wise to leave spaces for your balancing numbers, which is what I've done. So let's now have a look at see what the question tells us. So it also says that during this process the iron in the ilmenite is oxidized, so that must mean it goes from +3 to +4. Oh sorry, I beg your pardon, from +2 to +3 I should say. Okay, so here's our unbalanced equation. What we've got to be a little bit careful of is making sure that we're putting the right balancing numbers in. So there are 7 chlorines on the right hand side, and there are 3 oxygens on the left hand side. So let's do the oxygens first, because it involves reducing carbon monoxide, and the carbon is on its own, so we can easily deal with that. So by putting in 3.5 chlorines on the left hand side, we can balance for the chlorines on the right hand side. So it says the TiCl4 may easily be purified and separated because of its low boiling point. And you might have noticed that I put in liquid as its state symbol and not solid, because I had a little look at the question, and I just thought I'd not say anything about it till now, just to see if you can realise how it's quite important maybe to look at all the parts of the question before we start. So the 136 degrees C suggests a low boiling point for a metal compound, so therefore we can have a think about what type of structure and bonding might be found in solid TiCl4. So don't be fooled into thinking just because it's a compound of a metal and a non-metal that automatically means it's going to be ionic. This is the type of paper that's going to throw exceptions to the rule at you, as opposed to nice safe GCSE stuff. So the last type is going to be simple covalent based on the information that you're given. So with this next bit, it's got some thermodynamic data, so it's not surprising it's going to be a maths question and an enthalpy question. So I mentioned something called bond strength. Assume that that's the same as bond enthalpy for the sake of argument. So I'm going to do a Hess cycle for this one, and looking at the data it tells me that the delta RH for that particular reaction is minus 175 kilojoules per mole, which I'm going to pop in there as a reminder. So they have the enthalpy change of formation data for TiO2, and they have the enthalpy change of atomization of titanium solid. So atomization basically means the formation of 1 mole of gaseous atoms, so you're looking to go to Ti in gaseous form from Ti in solid form. So let's try and pull this together. To do a Hess cycle, what you've got to do is decide, is it combustion or is it formation data? So the first piece of data we can put in is the minus 939 kilojoules per mole to the minus 1. So we're looking for the delta FH of titanium chloride solid. So that's easy enough. That gives us minus 764 kilojoules per mole to the minus 1. So the slightly harder part is actually working out the average bond enthalpy. So we know the enthalpy of formation of TiCl4. So to relate the enthalpy of formation that we've worked out to the bond enthalpy, you have to base it on titanium 4 chloride being in gaseous form. So that's where the atomization comes in. As you can see, I've left the definition at the bottom left part of the screen. So essentially what the question is asking us is the titanium chlorine bond enthalpy when it's in the gaseous state. And therefore we need to think about titanium in the gaseous state and chlorine in the gaseous state. So that's where we start to bring in some other information we've been given. So this process starts by thinking about solid titanium being converted to gaseous titanium in terms of atomization, which I've left the definition for in the bottom left hand corner of the screen for you to refer to. Before doing the same thing to chlorine, or the 2 moles of chlorine gas that we have in the equation, So this allows us to construct 4 titanium-chlorine bonds in gaseous form and divide this enthalpy by 4 to get the enthalpy change for one of them, which is what the question wants. So here's the way you do it. So the atomization of titanium solid takes account of forming a gaseous titanium atom. If you do the bond enthalpy of a chlorine molecule twice, that converts 2 Cl2 molecules into 4 chlorine atoms in the gaseous state. And delta FH of TiCl4 is the formation of the gaseous TiCl4 as opposed to the solid TiCl4. So that gives us 1,721 kilojoules per mole to the minus 1. So the average titanium-chlorine bond enthalpy, or bond strength as they call it, is 430 kilojoules per mole. So now a brand new idea is actually put in. It's nothing to do with titanium. It introduces a new idea to do with paving blocks that can absorb Nox gases. So as a little side note, Nox gases are basically a family of nitrogen oxides. They're gaseous and form on room temperature. And they've been proven to cause respiratory problems such as asthma and bronchitis. They're commonly found in the exhaust emissions from diesel engines in large cities and built-up areas. So they're quite a serious environmental problem. So it's going back to fairly fundamental first-year ideas, not only because it's a dot-cross diagram, but also trying to combine the idea of a dot-cross diagram with a radical. So a radical, as you probably know, is a species containing an unpaired electron. And the fact it's a radical means that it's going to be quite reactive, and its reactivity, it follows from that, is its toxicity and its problems it causes when it's inhaled. So what I normally do when I'm asked to do this kind of thing is to think about which atom is more electronegative. The more electronegative an atom, the less likely it is to sit there with an unpaired electron. The more likely it is to force the other atom to go without an electron. So I'm going to start by assuming that nitrogen is the atom that has the unpaired electron. The next step I normally take in a dot-cross diagram is to think how many electrons does each atom actually have. So I'm assuming that you're with me when I say that I'm only referring to outer shell electrons here, so I'm going back to GCSE a little bit. So nitrogen has 5 outer shell electrons, oxygen has 6. So when I do my overlaps between my atoms, before I start putting electrons in, I'm leaving room for any double bonds which I think I might need as I start to deduce the structure. I'm going to start with my unpaired electron being on the nitrogen, and I'll try and build it up from there. So after about 30 seconds of head scratching, I realised that there's probably going to be a data covalent bond as well. So nitrogen has to have 5 electrons, so 5 dots. Each oxygen has to have 6 electrons, so 6 crosses, and I think we're there. So the next thing they ask you to do is to decide what possible bond angle you'd have here. So using normal valence shell electron pair repulsion theory, in other words, molecular shapes from your textbook, I'd normally go for maybe 2 bond pairs, 1 lone pair, because a double bond counts as a single bond. A double bond counts as a single bonding pair, and a data covalent counts as a single bonding pair. So the geometry we're looking at is loosely based on the trigonal planar shape. But what we've got to remember is that an unpaired electron repels less than a lone pair does, so the bond angle is going to be slightly bigger than 120 degrees. So from the choices that we're given, the most reasonable guess would be 135 degrees. So linking back to your work on radical substitution, because you've got 2 radicals meeting and then forming a molecule, you can treat this as a termination step, which gives you HNO3. So the next part talks about the superoxide ion, where the electron from hydroxyl radical can actually go and react to something else, such as oxygen molecules in the air, to make a superoxide ion, O2-. And then it asks what single charge species would you get by reacting O2 and nitrogen monoxide. So you should notice that NO3- is a fairly familiar species, nitrate ion, the nitrate 3, I think. Nitrate 3, let me just double check it in my head. No, sorry, that's the nitrate 5 ion. The nitrate 3 ion would be NO2-. Beg your pardon there, I should have been thinking a bit better on my feet. Okay, so the next one, part 3. So when they say the net overall equation, that means you've got to take all the things that are going on and try and work out what the combination of all of them would look like. So it's going to mean a little bit of cancelling. So let's start in red. Then we can switch to blue. Then we can look at the next species. And they also want from you the species being reduced in the equation. So the easy way to spot if there's redox going on is to look for an uncombined element which is not an ion. So I think we're looking at oxygen. So I'm just going to highlight it down there for you. So in this next question, what you're being asked to do is to take the substance or substances in a word equation and use them to construct a balanced equation. So all I've done there is put into an equation form what the question is suggested to me. So I need to know what, or need to work out rather, what the other product is. So seeing as one of the chlorines is used up, it's highly likely it's HCl. So what you've got to think about now is how you're going to balance that. And the easiest way to do it would be something like that. So in part H it gives you a reaction, which I'll just copy out for you so we can talk about it. And it asks you which of the following oxidation, reduction, disproportionation or nothing best describes that reaction. So because it's clearly talking about redox, the best thing to do is to assign oxidation numbers. So working on the premise that chlorine is -1, you can assign oxidation numbers to titanium accordingly. So 3 chlorines in TiCl3 will be +3, 2 chlorines in TiCl2 will be +2, and TiCl4 is obviously +4 because we've talked about it. So you've got simultaneous reduction and oxidation going on, which means it's disproportionation. Now the next part introduces entropy, which is something you might not have come across before. It does come up in the second year, but if you're taking this as a first year, you won't have heard of it. You may have done if you're doing physics, or perhaps done a bit of reading around, but it gives you a bit of information as to what it is. It's a quantitative measure of the change in the amount of disorder that takes place during a reaction. So the amount of disorder in the products minus the amount of disorder in the reactants, the difference, in other words, is the same as the change in disorder. So delta S is going to be what that means. So 2 moles of solid, which is an ordered state, becomes 1 mole of solid, which is the TiCl2, and 1 mole of gas, which is the TiCl4. So gas is more disordered than solid. So therefore, the delta S value will be positive, or it will increase. So the next part of part H asks you to think about the position of equilibrium if the standard enthalpy change of the reaction were negative. So the next part of the question asks us to consider a little bit about the equilibrium. So if the standard enthalpy change of the reaction was negative, the forward reaction is going to be exothermic, meaning that if the temperature is decreased, the position of equilibrium would move to the right. If the temperature increased, the position of equilibrium would move to the left. So all you're doing really is applying Le Chatelier's principle. So this next part, which is called part J, I'm not quite sure there isn't a part I can't see one, actually brings together several things that you've come across before. So K can be considered as similar to Kc, the equilibrium constant, in other words, temperature and Boltzmann distribution of molecular energies. So bringing all those ideas together gives the Arrhenius equation. So although the equation here is connected to Arrhenius, I'm not going to go into Arrhenius because you'll need to wait for that for next year. If you do want to find out about Arrhenius, you can go and look on lots of different YouTube clips. I've done a couple. There are other people who've done them as well. So that could be something to look at next year when you come back. But for now, let's just concentrate on the equation that we're given. So the trick to this question is to recognize the equation they give you as analogous to y equals mx plus c, because you're dealing with a straight line graph. So we can rewrite the expression like that. So if x is 1 over t, we can see this because of the x-axis being labelled 1 over t, then minus delta h over r is going to be the gradient. So if you look, on the graph you're given some x and y coordinates to make it easy for you, because obviously to get the gradient you have to do dy over dx. So you can put them in like that, which in turn gives us 18750 as our gradient. So by simply rearranging minus delta h over r, that gives us that expression, which in terms of a calculator value is positive, I should say, 155.8875 kilojoules per mole. But because 8.314 is quoted to 4 significant figures, so must our answer be. So to work out delta S, it's quite easy. We can use ln k as minus 12, 0.001572 is 1 over t, minus 18570 is delta h over r, like we've just calculated. So that gives us 17.475 as the value for delta S over R. So that allows us to work out delta S as 145.3, joules per mole per Kelvin. Let me just change my units there. Apologies for that. Okay then. The very last question is nice and easy. We're told that titanium 2 chloride has a melting point of 1035 degrees C, and that it also dissolves in molten calcium chloride. Both of these can actually be used to deduce that it's ionic, because I've asked you just to circle which of these structures it's likely to form. So only an ionic solid will dissolve in another ionic liquid, in the same way that non-polar solutes will dissolve in non-polar solvents. Polar solutes will dissolve in polar solvents.